It's now recording. So we are going to start on sets. Let's look at set theory. I just need maybe a highlighter. Okay, this one we do. Okay, so the definition for sets, a set is any well-defined collection of objects. So any well-defined collection of objects is what we call a set. So the elements of a set are the objects in a set. So there are things that we call elements. So those elements are the objects which are found in a set. If you say I've got a set of students, then the students themselves are now the elements of that set. So notation, there's the set notation, the way we use to write our sets. So usually we denote sets with uppercase. We denote sets with uppercase letters, elements with lowercase letters. So if the set is student, and then we use capital letters, maybe S, to represent the set itself, and then let's make sure that we are muted. It's Manners. Can you make sure that you are on mute? Also switch off your camera. These are things that we are trying to avoid for those people who will be joining late. Those are the ground rules. You need to make sure that you're on mute as well as your camera is switched off. I think this is supposed to be applied to everyone who is joining. Okay, so I was saying that if we've got a set of students, and then S maybe will be the letter representing the set, and then for the elements we use small letters like X, Y, Z, something like that. So X is an element of A, something like this. So this means that X is a member of the set A, and then here X is not a member of set A. So we can use member or element, it's just the same. So you can say X is not an element of A, or X is not an element, X is an element of A, and X is not an element of A. So this is the membership relationship. So you can use this symbol for that. And then there is the roster method. The roster method, it's a way of describing a set. So here you can say list the elements like this. That's how you use the roster method. You've got the name, a set A, and then it is the elements of the set will be within these curly braces, and the elements will be comma separated. We've got a lot of people who want to join here. This is what I was saying. You need to join earlier, so that it will be easier for us. So guys, let's make sure that we are all muted. Let's make sure that we are all muted. So that's what you do if you're using the roster method. And then the set builder notation, where you'll be given some sort of description, but it's not a description. So characterize all those elements in the set by stating the property or properties they must have to be the members or to be the elements of that set. So you can have A, here you can have A, and then you say that X is such that X is an odd positive integer less than 10. So in other words, this set A is going to take all the positive integers, but not all the positive integers, but all the odd positive integers which are less than 10, which means we are starting from 0 to 10, but you only want those odd positive integers between that range. So this kind of giving the set is what we call the set builder notation. And then there is the descriptive form, where you'll be given the description. So it's give a verbal description, like here we're saying X, such that A is the set of all integers from 1 to 6 inclusive, which means we are going to take 1 up to 6. just like that. From this, then you can build the set. So let's look at some of the common sets that we know. We have got this set, which is the set of natural numbers from 0 up to positive infinite. And then we've got this Z set, which is the set of all integers, whether a negative or a positive. If it is for positive, it will be Z and with a plus at the top. So we've got a Q, which is the set of rational numbers, and also we've got an R, which is the set of real numbers, and also C, which is the set of complex numbers. Why are we talking about this? Because when you're doing sets, you must be, maybe sometimes you see these symbols being used, you need to know what do they mean. So let's talk about what we call a null set and an empty set. There's what we call a null set and an empty, oh sorry, not a null end, but a null set or an empty set. So this is a set with no elements, often symbolized by this phi with a stroke. This one, this circle with a stroke, something like a phi, and then it can be also represented by two curly braces without anything in between. So this is called a null set. You can call it a null set or an empty set. So if you are given a question which will be talking about a null set, note that we are talking about an empty set. And then there's what we call a universal set. This is the set of all elements currently under consideration and is often symbolized by this U or this symbol. You can call it maybe something like an epsilon, but that symbol is the one that we use to show that this is our universal set. So we are saying the universal set is just the collection of all the elements under consideration for that question that you're dealing with. Maybe if you are looking at the students at a certain university, you are talking about all the students as the universal set. And then from there, we can talk about some of the subsets where we can have students who are in software engineering and other students IT engineering. These are now subsets, but the universal set is the set of all students at Zimbabwe Open University. So this is what we call the universal set. From there, you can come up with the small subsets. Then there's what you call a subset. So a subset, like this one, we are saying A is a subset of B. What it means is that we've got some of the elements which are in A, but these elements which are in A are also in B. And maybe B can have other elements there. So we say that A is a subset of B if X is an element of A, which implies that also that X is an element of B. That is, all the elements of A are also elements of B. So you must not have an element which is in A, which is not in B. Otherwise, it will be not a subset. So the notation for subset is very similar to the notation for less than or equal to, and it means in terms of the sets included in or equal to. So in other words, this A is a subset of B. It means that this A can also sometimes have the same elements of those in B. It is still a subset, because if we put those elements, if you take those elements in A and compare them with the elements in B, you see that all the elements in A are also in what? Are also in B. And then there's what you call a proper subset. A is a proper subset of B. We say that A is a proper subset of B if all the members of A are also members of B, but in addition, there exists at least one element C such that C is an element of B, but C is not an element of A. So in other words, we are saying A is not exactly equal to B, but we've got some elements which are in A, but these elements which are in A are also in B. So that's a proper subset of B. So A and B, they are not equal, and there is no chance that A and B will be equal on a proper subset. But we are saying all the elements in A are in B. But after that, B have got some other elements which are not in A. So B will be a bigger set than B will be a bigger set than A, but A, all the elements in A will be also in B. That's a proper subset. Then let's talk about what we call a finite set and infinite set. So a set S is said to be finite if it contains exactly m distinct elements where m denotes some non-negative integers. So we can say this element, this set is finite if we can have exact number of elements within that set. So if you are going to say the set S is a set of all students at Zimbabwe Open University, that set is finite because we know the exact number of all the students that we have. So in such case, we write that the modulus of S, which is the total number of all the elements within that set, will be equal to M, or number of elements in S. You can use this notation as well, is equal to M, which is the cardinality of S. You can call it cardinality of a set, which is the total number of elements within that set. So a set is said to be infinite if it is not finite. So it's like the opposite of finite. So, for example, the set of S of letters of English alphabet is finite because we know that A to Z is what is 26. We've got 26 letters or 26 alphabets on an English alphabet. So the set of positive integers, we know that it's infinite. We can start from 1 up to positive infinity. So that set is infinite. Then let's talk about equal sets. Let's talk about equal sets. So that there was someone. Richard Mufuro. Is that a hint? Do you want to ask something? Do you want to contribute?
Yes, sir.
Yes.
I didn't quite understand the difference between a subset and a proper set.
Okay.
Yes, because I heard, maybe I missed something. I heard you say for A to be a subset of B, all members of A should be also be in B.
Yes.
Then for a proper subset, I didn't get the difference.
Okay, the difference is that when you are talking of a subset is anything like all the elements in A are in what? Are in B. But you are not looking at, is B exactly equal to what? Equal to A. But when you're talking about a proper subset, you are saying these sets must not be equal. But you are saying all the elements in A are in B, which means B goes an extra mile after accommodating all the elements in A. That one is what we call a proper subset because those sets are not equal. So it means A is a proper subset of B. There is no chance that A will be equal to B. I don't know if you are answered there.
Thank you, sir.
Okay. Then let's look at the issue of equal sets. So two sets are equal if and only if they have the same elements, not the same number of elements, but same elements. If we have got a 1 in A, we must have a 1 in B. If we have got a 2 in A, we must have got a 2 in B. So therefore, if A and B are sets, then A and B are equal if and only if all elements in X, this is for all elements in X must be an element of A as well as X must be an element of B. So in other words, we are saying if X is an element of A, it implies that X is an element of B. If X is an element of B, it implies that X is also an element of A. So it goes both ways. It goes both ways. So the sets 125 and 251 are equal because they have the same elements. So take note that sets are not equal because they have got same number of elements, but they must have same elements, just like that. So the order in which So the order in which the elements of a set are listed does not matter. So also it does not matter if an element of a set is listed more than once. Let's make sure that we are all muted. Let's make sure that we are all muted. Nagaisa my headphones. So that feedback. So what we are saying is this set 1, 2, 2, 2, 2, 5, 5, 5 is the same as the set 1, 2, 5. Why? Because we've got same elements here in this set and in this set. So the issue of repetition does not matter. Otherwise, this set is just 1, 2, 5 because those are the elements that we have there. So sets can be represented graphically using the concept of Venn diagrams, named after the English mathematician John Venn. So guys, on the issue of Venn diagrams, you need to understand how to draw a Venn diagram. Maybe you need to understand the issue of intersection, union, the complements, all those things. You need to understand all those things on a Venn diagram. So in Venn diagrams, the universal set U, which contains all the objects under consideration, is represented by a rectangle. Inside this rectangle, circles or other geometrical figures are used to represent sets. And normally we do use circles. So sometimes points are used to represent the particular elements of the set. So normally you just write the elements within the set. So Venn diagrams are often used to indicate the relationships between sets. Let's make sure that we are all on mute. Let's make sure that we are all on mute. Let's make sure that we are all on mute. Butte, can you make sure that you switch off your camera? Butte Nkwas, can you make sure that you switch off your camera? Just click at the top here. You see the exactly. Thank you. Okay, let's talk about power sets. Let's talk about power sets. We talk about Venn diagrams later. So given a set S, the power set of S is the set of all subsets of the set S. So any possible subset that we can create from S is what you call the power set. So yeah, say any subset, not any subset, but a collection of all those subsets is what we call a power set. So given a set, you need to generate all possible subsets. And then the collection of all those subsets is what we call a power set. So the power set of S is denoted by P of S. What is the power set of the set 0, 1, 2 of the set with elements 0, 1, 2? Which means you need to create all possible sets of this set. Maybe you're going to have a set with only a 0, with only a 1, with only a 2, and even this set itself. And even the empty set is part of the subsets that we can create from this set. So the power set of 0, 1, 2 of the set with the 0, 1, 2 is the set of all subsets of this set. And if you look at it, we've got the empty set first as the set as a subset of this set. And then we've got the set with only 0, the set with only 1, the set with only 2, and also the set with the 0, 1, and also the set with what? With the 0, 2. So you put all the combination that you can have. Also the set with 1, 2, as well as the set with the 0, 1, 2. So the collection of all those sets is what you call the power set. So note that the empty set and the set itself are members of a power set. So you need to know that, guys. Otherwise, you'll be asked to create this, to come up with this power set. Maybe you forgot to put the empty set and that set itself. So let's look at what we call a Cartesian product of this power set. So guys, if you are being asked to find a power set, that's what you do. You list this. not to give us the total number of possible subsets that you can create and say this is the power set. No. I'm sure it's unspeakable on that one. So let A and B be sets. So the Cartesian product of A and B, denoted by A cross B, we say A cross B, not A times B. A cross B is the set of all ordered pairs A, B, where A is an element of B and B is an element of B. So hence A cross B is such that A, B, it will be a collection of these sets A, B, such that A will be an element of set A and B will be the set element of set B. So if you are given two sets and you are trying to do A cross B, something like you are multiply, but it's not multiply. You are saying the first part will be coming from the set A, and then the second part will be coming from B. So it will be like a collection, just like what we are doing on a power set. So what is the Cartesian product of A with the elements 1, 2, and B with elements A, B, C? So the solution is the Cartesian product of A cross B is, so if you look at it, guys, you are saying 1A, which means what you do is you take 1 and match it with all the elements in the next set. So I'm going to have 1A and then 1B and then 1C. After that, you do it for 2, it's 2A and then 2B and then 2C. That's the Cartesian product. So note that the Cartesian products of A, B, and BA are not equal unless if A is an empty set and B is also an empty set. So that A cross B will be an empty set, or A is equal to B. So in other words, guys, A cross B is not equal to B cross A unless both A and B are empty sets. Hope it's unspeakable. So let's look at this. Now, instead of A cross B, now we've got A cross B cross C. Now we've got A cross B cross C. Now we've got A cross B cross C. What are we supposed to do here? So the solution, if you look at it, at A, you've got 0, 1, here you've got 1, 2, here you've got 0, 1, 2. So the Cartesian product of A cross B cross C consists of all ordered triples from A, B, C, where A is an element of A and B is an element of B and C is an element of C. So it will be a collection of these three elements from three different sets. A will be coming from this, B will come from this, and C will be coming from this. So if you look at this, we have got 0, 1, 0. How are we getting this 0, 1, 0? We are taking this 0 and then match it with this one, and then match it with this 0. And then the next thing, you take this 0 again, you match it with this one, and then you match it with this one. That's why we've got this 0, 1, 1. And then after that, you take this 0, you match it with this one, and then you match it with this 2. That's why I've got 0, 1, 2. After this first cycle, you move to this, because we have done from 0 and then match it with 1 and then match it with everything else here. You need to match this 0 with the 2 and everything else here. That's how you do the cross product. After that, you move to 1 and match it with this and everything else, then 1 with this and everything else. Then you are done. So we have done with the 0, we match it with the 1 and everything else. Then we are going to match 0 and then 2, 0, 2, and then we match it with this 0. That's why I've got this 0, 2, 0. After that, we go from 0 to 2 and then match it with 1. And then after that, 0, 2, match with 2. That's why I've got 0, 2, 2. So now we have matched 0 with the 1 and everything else, 0 with the 2 and everything else. It's now the turn of this one being matched with 1 and everything else. and then this one matched with the 2 and everything else. If you look at it, we've got 1, then 0 here. After that, it's 1, then 1, then 1. And then after that, we've got 1, 1, 2. After this, you are going to make this one and 2 because we have matched this one and 1, this one with this and everything else here. So you need to match this one and 2 and everything else here. So I'm going to have 1, 2, 0. After that, it's 1, 2, 1. After that, it's 1, 2, 2. Then we are done with the cross product. And note that when A, B, and C are sets, A cross B cross C is not the same as A cross B cross C. You need to take note of that. But mostly we are going to give you such kind of cross products. I don't know if I've got any question on how you can do a Cartesian product given these 3 sets, given these 3 sets. If there is any question, you can raise your hand. Otherwise, you are going to do set operations. Yes, Walter, I'm seeing a hand. You can unmute yourself and contribute if it's a contribution or ask if it's a question. Walter, you're still muted. Okay. Maybe I can just lower your hand if you are not saying anything. So 2 or more sets can be combined in many different ways. Let's look at set operations. So for instance, starting with the set of mathematics majors at your school and the set of computer science majors at your school, we can form the set of students who are mathematics majors as well as computer science majors, or the set of students who are joint majors in mathematics and computer science, or the set of all students not majoring in mathematics. Walter, do you want to say something?
Yes, sorry. Yeah, I wanted to ask about the Cartesian what, which is the A cross B bracket cross C.
A cross B bracket, then cross C.
Yeah, I wanted to ask. We solve A cross B,
and then
and
you
then you
cross
solve.
yes, and then you cross it with what? With the C. But the issue is do not stress yourself much on those ones, because the dimension it is going, we are not going to ask you on that one. But otherwise, that's the issue. That's the difference between this and this.
Okay, thank you, sir.
Okay. Then let's look at the issue of set operations. Let's look at the issue of set operation. So A union B, we've got the set union. So A union B is the set of all elements that are in A or in B or both. That's the union. So an element X belongs to the union of the sets A, B, if A and B, if and only if X belongs to A or X belongs to B. So that is A and B is equal to X is such that X is an element of A or X is an element of B. So on a Venn diagram, this what would be. If you look at it, you shade both A and B. That's the union. So if you are going to be asked of a set union, you take all the elements in A and all the elements in B. You do not necessarily need to repeat those elements which are at the intersection. Just write them once. Excuse me. So that's how you represent it on a Venn diagram. Remember on your assignments, there was a question which was requiring you to shade the required region. So normally this is how you do it. So if it is a union, this is how you do it. You shade both A and B, because we want all the elements in A and in B. That's the union. So any element that we're going to pick within the union, it's either it is in A or it is in B, just like that. So this is similar to the logical or operator. So the union of the sets 1, 3, 5 and 1, 2, 3 is the set 1, 2, 3, 5. That is 1, 3, 5 union 1, 2, 3. So this is what you get. You are just going to take this and join it with this. So guys, you are not going to repeat these three because it's in both sets. So these are the elements which are at this region, at the intersection, which are in both A and B. So you just write them once. That's why for this 1, 2, 3, 5. So the union of the set of all computer science majors at your school and the set of all mathematics majors at your school is the set of all students at your school who are majoring either in mathematics or in computer science or in both. So let's talk about the intersection, the set intersection. So it's the set of all elements that are in both A and B, denoted by A intersecting B, this symbol. So an element X belongs to the intersection of the sets A and B if and only if X belongs to A and X belongs to B. And if you look at that, it's an AND operator which is there. So in other words, X must be an element of A and X must be an element of B on X intersection B. If you have X in this intersection B, it means that X is an element of A at the same time is also an element of B. It's a must. So it falls under this region. So if you are being asked to shade A intersecting B, that's where you shade here this region, which is the intersection of B. So these elements are both in A and they are also in what? In B. So the shaded region represents the intersection of A and B. This is similar to the logical AND operator. Note that two sets are called disjoint if their intersection is the empty set, e.g. let A be 1, 3, 5, 7, 9 and B be 2, 4, 6, 8, 10. Because A intersecting B is an empty set, it means that A and B are disjoint. So disjoint sets, guys, are those sets which doesn't meet here. So if you look at that, they do not intersect each other. So they are disjoint sets. We call them disjoint sets. In other words, there are no common elements in these two sets. So they are disjoint. So a complement, the set complement, a complement or not A is the set of all elements in the universal set, but not in A, denoted by A bar, this one, or it can be given A, that's the A complement with this power 1. It's an A complement, or you might be given A with a bar at the top. So an element belongs to A complement if and only if X is not an element of A. So in other words, X is an element of the universal set, but X is not an element of A. So when you're talking about a complement, we are talking about the elements which are within the universal set, but they are not in that set that we are talking about, specifically the subset that we are talking about to the universal set. So the shaded area outside the circle representing A is the area representing the A complement. So if you are looking at that at this Venn diagram, all this shaded area is the complement of A. All the elements which are outside A, but they are within the universal set. So if you are talking about the set of all students at Zimbabwe Open University as the universal set, and then maybe A is the set of those students who are doing IT. We are doing IT, which means we are saying a complement. We are talking about all other students who are not doing IT. So we just shade outside what? Outside A. So let A be equal to A, the set of vowels, where the universal set is the set of letters, the English alphabet. Then the A complement now includes all the elements, all the members of the alphabet which are not vowels, which are not I, E, O, O, or A, E, I, O, U, this one. So that's this one will become the what? The complement of A will become the complement of A, just like that. I think this one is very, very simple. So the complement operator is similar to the logical not and is reflexive. And this is the complement of A complement is also equal to A. If you want the complement of A complement, you are going to get an A. You shade this one because we are saying the complement of the complement of A. So let's look at what we call set difference. Set difference. So the set difference A minus B is the set of elements that are in A with those that are in B subtracted out. So we are looking at those elements which are only in A and not in the other set that we're talking about. So another way of putting it, it is the set of elements that are in A but not in B. So A minus B is just A intersecting B complement. So in other words, you just need to take all the elements in A and then you remove all the elements in B there. So the difference of set A and B is sometimes denoted by A then backslash B. So an element X belongs to the difference of A and B if and only if X is an element of A and X is not an element of B. So that is A is an element of B and X is such that X is an element of A and X is not an element of B. So this is where we shade. If you want to shade A minus B, this is where you shade. If you want to shade A intersecting B complement, this is where you shade. If you look at it, B complement are all the elements which are outside of B, right? Which are outside of B, all these elements which are outside of B, including those which are in A. So when you are talking about A intersecting B complement, it means you are talking about where they intersect each other. So the elements in A are all the elements here. But when you're saying intersecting B complement, which are the elements which are common in A and also in B complement are these only elements which are only in A, this part. So this is where it is coming from, this A intersecting B complement. So A minus B is just identical to A intersecting B complement. And we are taking those elements which are only in A. So take note of this when you are doing those questions in assignment where you'll be asked to shade some portion. So there's what we call asymmetric difference. Asymmetric difference. So given two sets, the asymmetric difference, the asymmetric difference is the set of elements that belong to either one or the other set, but not both. So X is such that X is an element of A or X is an element of B. So it can be expressed also in the following way. A union B minus A intersecting B, or A minus B union B minus A. In other words, we're just talking about the elements only in A and only in B, but not in both. So I'm just going to remove the intersection, this intersection, and then we're going to be left with elements either in A or in B as the symmetric difference. You are just going to take away those elements which are in between. So this was an exercise. This is an example where you have got the universal set 1, 2, 3, 4, 5, 6, and then you've got A with 1, 2, 3, and B with 3, 4, 5, 6. And then you are being asked to find A intersecting B. So if you are looking at A intersecting B, you want those elements which are common in A and B. And if you look at it, these three is only which is common. So A intersecting B, you get a 3. Then A union B, so it's either A or B. So I'm just going to join these two sets. So you're going to get 1, 2, 3, 4, 5, 6, which is almost the universal set itself. And then after that, we've got a B minus A. B minus A, we just want elements only in B subtracting A, which means we want only elements in B, but not in A. So if you look at it, these 3 is also in A, so you do not want it. But 4 is not in A, and 5 is not in A, and 6 is not in A. So you're going to get 4, 5, 6. A minus B, you want elements which are in A, but not in B. This one is in A and is not in B. And then we've got a 2, which is in A but not in B. So here there's need of adding a 2. This answer is wrong. We need to add a 2 there. So that's the answer for A minus B. And then for B complement, all the elements which are in universal set, but they are not in B. If you look at it, 3, 4, 5, 6, they are in B, but those elements which are not in B, but they are in the universal set are 1, 2. So that's why we've got this one too. And then you want the elements which are in A only and B only and not both. So at Suda Sudipa intersection. So 3 is common, so we remove it from our set. So you just take the union but removing those which are in both. So we're going to be left with 1, 2, 4, 5, 6. I think it's simple and straightforward. So this is a practice where you have A is 1, 2, 3, 4, 5, and B is A, B, C, and then you are being asked to find A minus B, A, union B, A cross B, and then A intersecting B. What's A minus B from this? From what? From this? What's A minus B? Just need to raise your hand. A water. What's A minus B?
Yeah, 1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yeah.
Exactly. Except those are the elements which are in A but not in B. Thank you for that. You can lower your head. And then let A be the set of students who live within 1 mile of school, and let B be the set of students who walk to classes. Describe the student in each of the sets, in each of these sets. So you need also to look at description of these sets. If you are saying A intersecting B, which means we need all the students which are within 1 mile. This is a set of all the students which are within 1 mile and the students who walk to classes. So that's the description that you need to give there. And then you need to practice to draw the Venn diagram. Maybe I give an A intersecting B union C. You must be able to shade the required region of this sets. And then that's all on sets. That's all on sets. I don't know if I've got some questions, but that's all on sets. I don't know if I've got questions on the sets. That's all what I have for this lecture on sets. Maybe I forgot to tell you that on your portal there is I'm sure there is a part which talks about set identities, I'm seeing that it wasn't covered in this slide. You need to really look into set identities. There is a question in assignment which was talking about set identities. I'm sure you can deduce from the given set identities, De Morgan's laws and all other laws which are there. You need to be able to apply them and solve that question. I think it will be enough for you and for your exams. I don't know if I have questions before looking at on our unit 3, which is relations. Unit 3, which is relations. Want to look at relations. Okay, so let's look at relations. Let's look at relations. By the end of this unit, you should be able to describe the concept of relations between two sets, use the appropriate methods for representing relations, explain some of the properties of relations. I'm sure this one was it also part of your assignments? I'm sure it was part of your assignments. Sit assignment 1. Don't remember. Okay, this is what I was talking about. Some of these questions you must be able to do them. Oh, this was part of assignment of A cross B cross C. Okay. It was part of the assignment, so I'm happy that we have revised that one as well. What else? This one was also part of the assignment, so you have revised it as well. It's part of the assignment one. It's already submitted. Okay, so these are the relations. So this is what we are going to do. So after this slide, you must be able to answer such kind of questions, and even this one, matrix representation for relations. So you must be able to answer all these ones. Otherwise, you need to ask. So this was a part of your assignment. I'm happy you've covered almost part of assignment one. So you just need to go into a revision on that one. Just need to go into a revision on that one. Allow me to check so that I know what you are supposed to do. Okay. We need, okay, these are the issue of relations. Yeah, for this one, I'm going to do it later. Okay, you're going to do this one later. Don't know what happens with the Adobe tables and tendons of just. Okay, so let's look at these relations. So let X and Y be two sets, a binary. So a binary relation R from X to Y is a subset of the Cartesian product X cross Y. If X is an element of R, we write X is related to Y or X R Y. So guys, we've done the cross product and the Cartesian product between two sets. And we found out that when you're doing the cross product, you match the first elements with those in the second in the second set. So what it means when I talk about relation, we're just talking about the subset of all those of all the subsets that we get when you're doing the cross product. So this is another definition. The set X is an element of X. XY is an element of our relation. For some Y is an element of Y, which means this Y will be belonging to the set Y. It's called the domain of R. The set Y is an element of Y, where XY is an element of R. For some X is an element of X. Is called the range of R. Why? Because Y will be our range, where X it will be our domain. We put X and we get Y, something like that. So if X is a set of students, for example, X, we've got Jimmy, Sheila, Shami, and Surai, and Y is a set of courses, Y, like computer science, maths, art, history. So a relation R between X and Y indicating courses taken by students, because we're saying they set cross this, can be written as Jimmy, then computer science, Sheila, then maths, Jim, then art, Shami, history, Shami, computer science, something like. So it's a cross product, like what we have been doing. I just need a highlighter. Okay. Just like that. So we can represent a relation in above example pictorially by using an arrow diagram, just like this, where you can have Jim, then doing computer science with Sheila, doing mathematics. Jimmy also is doing art, and Shami is doing computer science and is doing history, something like that. So that's how you present it. So example 2, suppose X will be equal to 3, 4, and Y will be equal to 3, 4, 5, 6. So if you define a relation R from X to Y, by XY is an element of R. If X divides Y with remainder 0, we obtain. So before that, when we're doing cross product, there wasn't a rule. We're just doing the cross product where you need to match these 2 with everything, 3 with everything, 4 with everything. And then from all those answers that we have, we are saying we just need only a collection where X divides Y with the remainder 0, which means you only want where you've got this X can divide into Y, leaving a remainder 0. So that's why I've got only 2, 4, because if we put it 2 into 4, we can get 2 with the remainder 0. Then we've got 2, 6, 3, 3, because 3 into 3, you get a remainder 0. 3, 6 as well, and 4, 4. So if you look at that, these first elements are coming from X, and then these ones are the range are coming from Y. So 2, 4, we are talking about this 2 and this 4, not this 2 and this 4. So that's this 2, 4. And then We can take this 2 and 6. That's why I've got 2 and 6. And we can take this 3 and this 3. That's why I've got this 3, 3, and then 3 and a 6. And then what else? 4 and this 4. So this makes our relation. So the relation is being built on this relationship that x divides y with the remainder 0, giving remainder 0. So the domain R is the set 2, 3, 4, and then the range of the relation R is the set 3, 4, 6. If you look at it, the range is what? It's 3, 4, and 6. If you look at it on the set of Y, we only have 3, 4, 6, and then the domain we only have 2 and 3 and 4. So that one is the domain. Those values that we are putting in our relation to give us the output, and the output is our range. So it can be represented pictorially using this diagram where for the set X and the set Y, and then we link them through this relationship. There's a link between 2 and a 4, so you must see a link between 2 and a 4. There's a link between 2 and a 6, so you must see a link between 2 and a 6 from this to this. Both this is our domain and this is our range, something like that. So this is an exercise. Suppose that, right, we have got 1, 2, 3, 4, 5, and then y 3, 6, 9. Write a relation R between set X and Y defined by, firstly, X, Y is an element of our relation R if X is on less than Y. And then X, Y is an element of R if Y is equals to 2 times X. So what can we have as our relation at A here? What could be our relation? What could be our relation? What could be our relation? I just want maybe one to tell us if you have the direction. Maybe it's too early. It's okay. Maybe it's too early. But what you're saying is we are just combining this. I'm seeing that we only have water here. I only have water.
Yeah, I want to try so that ndobva ndaona apa panenge ndisina kunyatsokunzwisisa ndotozvibatira ipapa.
Okay, it's okay, no problem.
Yeah, the relationship where X is smaller than Y. Then we compare, we take 1 and then compare with 1 on X, then we compare with the values on Y.
Yes.
Then we see 1 is less than 3. So
yes.
we say 1, 3. Then we take 1 again and compare by 6. We get 1, 6. And 1 by 9, we get 1, 9. 1, 9. Exactly. And then we take 2. We compare by, yeah, we see it's less than 2.
Yeah, so we have 2, 3.
Yeah, 2 by 6.
Yes.
We get 2, 6. 2 by 9.
We get
2, 9.
Exactly.
And then 3. 3 by 3 we see is not less than Y.
Exactly.
So we leave it. And then 3 we compare by 6. It's okay. We take
then
it.
We get 3, 6.
3, 6. And 3 by 9, we get 3, 9.
Exactly.
Then we go to 4. We take 4 by 3. It can't. 4 by 6, it's okay. 4, 6.
So you get 4, 6.
Yeah. 4 by 9, we get 4, 9.
And then we get 4, 9.
And then we go for 5. 5 by 3. It's not less than. It can. 5 by 6, it's okay.
5
and then
5 and 6. Oh, we are saying 5 is less than. Yeah. That's it. You can take 5, 6, and 5, 9.
Yeah.
Yeah. So that's it. Thank you for that. So that's how you find that. And then for the second one, is that we are saying y must be twice on x. What it means is that whenever you get your y, the y must be always 2 times x. That's how you build this relation. Y must be 2 times x. So the first value that you have, if you multiply it by 2, you must get a what? You must get a y. So if you take 1, if you multiply it by 2, is there any value that you can get? No. If you get 2, if you say 2 times 2, you get a 4. Is it equal to y? No. If you get a 3, if you say 3 times 2, you get a 6, which means you can match 3 and 6 there. If you say 4 times 2, you get 8, so there's no 5 times that way you cannot get. So it's something like we are saying you are taking the value in x, you multiply it by 2, then you get a what? You get a y, something like that. So that's how you do it. That's how you do it. So inverse relation, there's what you call an inverse relation from x to y. So the inverse of relation denoted by r to the power minus 1 is the relation from y to x defined by r to the power minus 1. Then yx is such that xy is an element of r. So whenever you have xy, if it is an inverse, it will become yx. So you've got 2, 3, 4, and y with 3, 4, 5, 6. So if we define a relation r from x to y, by xy is an element of r. If x divides y, we obtain 2, 4, and 2, 6. Like we are saying, x divides y with the remainder of 0, give a remainder of 0. So this is what you get. So the inverse, you just take this 4 and put it here. So it will become 4, 2, 6, 2, 3, 3, then 6, 3, then 4, 4. That will become your what? That will become your inverse. So the inverse will become 4, 2, 6, 2, 3, 3, 6, 3. So you are just reversing. Your range will become your domain become your range. Then there's what called the composition of relation. Let R1 be a relation from X to Y and R2 be a relation from Y to Z. So the composition of these two relations denoted by R or R1 is the relation from X to Z defined by R or R1 is such that XZ and is such that you have xz as the final, so that xy is an element of r and yz is an element of r2. For some, y is an element of y. What it means is we are saying if x is related to y and y is related to z, then we must also get x what? Xz. That's the composition. Because you already have the link between x and y. And also have the link between y and z. It means that there is a link, also a link between x and z, because you can go from here to here to here. That's the composition of a relation. So example, suppose that we have got two relations, R, this is the relation R that we have, and this is the relation R2. So from the definition, if you look at it, the relation can be represented pictorially. Like here, you've got 1, 2, then you match 1 with the 2 because it's X and Y. Then you come also on R2, you match this Y and Z because R2 is relation between Y and Z. R1 is the relation between X and Y. So here you match 1 and 2, you match 1 and 6, you do match 2 and 4, 2 and a 4, then 3 and a 4, just like that. After that, you match this one, 2 and a U, and whatever. So at the end, the composition of this will become 1 and U, because from here, you can go from 1 to U straight through this link. So it's just a matter of matching. Whenever you've got a link between from X to Z through Y, you match the elements from XZ, from X and Z, just like that. So this will become your result. You have 1U, 1T, 2S, 2T, 3S, 3T, and 3U. I thought maybe there's someone want to join. So that one will become your composition of those two relations. If you look at it, we have actually eliminated which is the y which was supposed to be here. So we are now having xy, but this y is our z. If you look at it, this is UST, which is our set. So there is a relationship between X and Z. So that's the composition. We were having a relationship, this R1 with a relationship X and Y, and this R2 a relationship with Y and Z. And then from there, you can build the relationship of X and Z through this Y. And that's what we have done. If you look at it, we are going to have 1U, and also we're going to have 1T through this 6 here. We have got 1U, 1T. If you look at it, we can have 2S, and also can have 2T, something like that. 2S, 2T. So that's what you'll be doing there. So let's look at this, which are very, very important part of relations. Let's talk of relations on a set, relations on a set. Let's talk of relations on a set. Thought maybe there's someone was trying to join. So let's talk about relations on a set. We have got the reflexive relation, symmetric relation, antisymmetric, and transitive relation. Those are only relations on a set that we're going to talk about, the types of relations on a set that we're going to talk about. Those joining, make sure that you are on a mute. Also, your camera is switched off. Okay. So, definition of a relation on a set. A binary relation R on a set X is a relation from set X to a set X. So if you are saying a relation on a set itself, it would be a relation from X to X. So let R be the relation. Both can have a relation from one set to another set, which is from A to B. And then the relation in a set itself, it will be a relation from set X to set X, which means X is your domain at the same time is your range. So it's just the same with what we are doing here, but only that with what we are doing here, but only that we're having X and Y. But here we are saying we are only considering this set alone. So we are matching X and X, just like that. So for example, here we've got X with 1, 2, 3, 4, 5 defined by X. Y is an element of R if X is less than or equal to Y. So XY is an element of X. So then the relation will be like this. We are saying X must be less than or equal to Y. But these XY are both elements of X. What it means is that the value that we're going to take for X and the value that we're going to take for Y is the same set. So in other words, we are having a duplicate of a set, which means we're going to have this set 1, 2, 3. I'm writing using a mouse. My machine is not a touch screen, so allow me to write things which are not easier to read. So 4 and 5. So if you look at this, so in other words, we are duplicating this set. So I've got this set X and this set X, which is this set itself. And then we are going to check if X is less than or equal to Y. If X is less than or equal to Y, then we take that value. So you can check Y is less than or equal to 1 is less than or equal to 1. Yes, that's why you have this. 1 is less than 2. Yes, that's why you have this. 1, 3, 1, 4, 1, 5. Then 2 is it less than or equal to 1? No. 2 is it less than or equal to 2? Yes, that's with 2, 2, 3, 2, 4, 2, 5. Then 3 is it less than or equal to 1? No. Less than or equal to 2? No. Then we have 3, 3, then 3, 4, then 3, 5. Then is it 4 less than or equal to 1, 2, 3? No, but we have 4, 4, and then 4, 5. 5 is less than 1, 2, 3, 4. No, but you have 5, 5. If you look at this one, this relation is only a set X only. So you are just taking this set and map it to itself. So that's the relation on a set. So there's what you call reflexive relation. What is this thing that we call reflexive relation? If a relation is said to be of type of reflexive, so you need to understand reflexivity. So a relation R on a set X is called reflexive if X are element of R for every X is an element of X. So in other words, if you have got a set with 1, 2, 3, 4, you must have 1 matched to itself, 2 matched to itself, 3 matched to itself, 4 matched to itself for that relation. If you are not going to have that, then that set is not reflexive. So a relation R on a set A is called reflexive if AA is an element of relationship for every A in the element in the set A. So this is what we are talking about. So for this example, for example 2, let's look at this one. Consider the following relations on 1, 2, 3, 4, on 1, 2, 3, 4. So you've got this set 1, 2, 3, 4, and for the relation R1, R2, R3, R4, R5, R6 being built on this set. So it's a relation being made from this set to this set itself. So we need to pick from this one which ones are reflexive relations. So if you look at relation 1, is this a reflexive relation? Let's look at it. We've got 1, so we must have a 1, 1. We've got a 2, so we must have a 2, 2, which is here. We've got a 3, so we must have a 3, 3. No, we do not have that. So when you see that we do not have 3 weights mapping to itself, then that relation ceases to be a reflexive relation. So that relation is not a what? It's not a reflexive relation. So there's no need of checking 4, 4, though we have this 4, 4, but we do not have a 3, 3. So R1 is not a reflexive relation. Why? Because we do not have a vertex 3 mapping to itself, but element 3 mapping to itself. And then let's look at R2. R2 is not a reflexive relation. Why? Because you have got 4 elements, but you only have 1, 2, 3. So it means that whenever, even if it was going to be 1, 1, 2, 2, 3, 3, still we need 4, 4. So this one, it can't be to be a reflexive relation. We only have 1, 1. So it not have a 3, 3, a 2, 2, a 3, 3, and a 4, 4. So that's your reason to reject this R2 as a reflexive relation. Then R3, is this R3 a reflexive relation? You've got a 1, 1. Let's check for a 2, 2. Yes, we've got a 2, 2. For a 3, 3. Yes. For a 4, 4. Yes. So this one qualifies to be a reflexive relation. What about R4? Is R4 a reflexive relation? Is R4 a reflexive relation?
No,
Why?
because we don't have 1, 1. We don't have a 2, 2. We don't have again a 3, 3. We don't have a 4, 4.
Thank you. Thank you, Lynette. That's it. Thank you, Lynette. So this one cannot be a reflexive relation. So you can look for a reflexive relation at what? At R5, is this a reflexive relation? 1, 1, yes. And then 2, 2, yes. Then 3, 3, yes. And then 4, 4. Yes, this one is a reflexive relation. R6, it's not a reflexive relation. R6 is not reflexive relation. So let's look at symmetric relation. Way to be called a symmetric relation. Why it can be called a symmetric relation. Okay. So a relation R on a set X is called symmetric if for all X, Y are element of X. If XY is an element of R, then Y is an element of Yx is also an element of R. So for it to be a symmetric relation, whenever you have got an xy, you must have a yx. Whenever you have got a xy, you must have a yx. So in other words, we need a relationship that mapped from this side to that side, and then from that side to that side, going backward. That's the symmetric relation. So R is not symmetric if and only if there are elements A and B in A such that AB is an element of R, but BA is not part of the what of the relation. So whenever you've got AB and then you do not have a BA, that relation ceases to be a symmetric relation. I think that's the simplest way to define it. So consider the relation R on X, A, B, C, D, which is our set. Given follows, we've got A, D, B, C, C, B, D, A. And you are being asked, is this a symmetric relation? You have an AD, right? and then here you've got a BC, and here you've got a CB, and here you've got a DA. So whenever you've got an AD, you must find DA, which is this one. Whenever you've got a BC, you must find CB, which is this one. Then you can say the relation is symmetric, because for all x and y, when y is an element of R, we have yx as the element of R. In this case, DA, CB, BC, and AD are all in R. So the set is the R, or the relation R, is symmetric. So now we are given this. Let A be 1, 2, 3, 4, and define relation R1, R2, R3, and R4 on A as follows. R1 is 1, 1, 1, 3, 2, 4, 3, 1, and 4, 2. And then we've got 1, 1, what, blah, 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 up to R4. And then we want to check if R1 is symmetric, R2 is symmetric, R3 is symmetric, and R4 is symmetric. If you look at this, R1 is R1 symmetric. If you look at it, we've got 1, 1. So guys, whenever you've got 1, 1, it means that you already have, if you have 1, 1, it means you already have A, B, and BA. Why? Because this one is mapped to 1. You can also say this one is already mapped to 1. So this one, 1, 1, and then you have got 1, 3, you must have a 3, 1. Then whenever you have a 2, 4, you must have a 4, 2. Then which means R1 is a symmetric relation, because for every AB that you have in R1, you also have BA in that. So that's how you justify. You need to justify why are you saying this relation is symmetric. So that's how you justify that R1 is symmetric. And then let's look at R2. Is R2 symmetric? We've got 1, 1, 2, 2, 3, 3, 4, 4. R2 is symmetric. Why R2 is symmetric? Because for every AB that we have, also have a BA. Because we've got this 1, 1 is our AB, and this 1, 1 is also BA, something like that. Because 1, 1 is as good as we are going forward or the reverse. So 2, 2, 3, 3, 4, 4. So it qualifies to be a symmetric relation. Then for R3, we've got 2, 2, 2, 3, 3, 4. This one is not a symmetric relation. Why? For 2, 3 that we have, we do not have a 3, 2. For 3, 4 that we have, we do not have a 4, 3. So R3 is not symmetric relation because 2, 3 and it's not an element of R3, but 3, 2 is an element of R3. So let's look at R4. R4, is it R4 a symmetric relation? We've got 1, 1, good, 2, 2, good, 3, 3, good. But here we've got a 4, 3, but we do not have a 3, 4. So 4, 3 is an element of R4, but 3, 4 is not an element of R4. So this is not symmetric. So that's all about symmetric relation. If there are questions, you need to ask, because now we are going to look at antisymmetric relation. We are going to look at antisymmetric relation. What is that, a hint?
Yes, say ndokumbira mudzokere pa question reflective. I mean reflexive.
Reflexivity, okay.
Yeah. Apa pandoda kubvunza kuti apa paka pane tanga tichiti inofanira kumepa on itself handiti kuti 1 1 2 2 chichichi. Let's say tabvunziwa tawana kuti pazopindiridzira imwe isina kumepa, tinoti flexive here kana kuti haisi, cause uko kumberi uko ndaona kuti kana paita imwe iri wrong 1 munoti haisi.
For reflexivity, we are just saying for that relation, every element in X must be mapped to itself. So in other words, this is good. Check on the reflexivity. You are just going to check. We have got 1, 2, 3, 4, which means for that relation which is going to be generated from this set, for it to be reflexive, within that relation, we must have 1, 1, 2, 2, 3, 3, 4, 4, and then anything can be added on.
All right.
And on symmetric, we are saying whenever you have AB, you must have BA. Start making sense. If you have a 2, 3, you
Yeah,
must
yeah.
have a 3, 2 in that relation. If there is no 3, 2, then that relation is not symmetric. So if you are having a 1 and a 2 here, so and a 2 here, so if you have an arrow going from this direction, we must also have something going this backward. If you do not have this, then the relation with the that relation that you're talking about, it's not a symmetric relation. That's the thing there.
Yeah, thank you.
Okay, Steven.
Can we say asymmetric about it's more of finding an inverse of a set
Asymmetric.
or symmetric? But can I see inverse yayo? I see symmetric.
Can I see inverse? Is symmetric? Don't know. Maybe you are trying to make things complex. But it's just the same thing. If you are saying you are going from this direction to this one, the inverse is going back. Yes, you can say it's not symmetric relation, but I think it's just is without including another concept of finding the inverse and what. We are just saying if you have got A mapping B, and then you must also have B mapping A. In other words, you can go forward and going backward. You are going to see it when you're going to draw some diagraph. There's a question. I'm sure in the assignment there was a question which was asking you to draw some diagraph, and then you comment on a diagraph. Is this a reflexive? Is this what relation? Something like that. So these are things that we'll be looking at. If you have got at every vertex, for symmetric, you'll be saying if you have an arrow going to another vertex, you must have an arrow going back to that vertex from the final vertex. From this vertex to here, they must have another arrow going back here. If you do not have this arrow going back here, it means that relation is not symmetric, something like that. So that's it. So let's look at what we call anti-symmetric. So there is symmetric relation and anti-symmetric relation. Take note of this. Anti-symmetric is not the opposite of symmetric relation. Take note of that. It's not exactly the opposite of symmetric relation. So a relation R on a set X is called anti-symmetric if for all xy is an element of X, when xy is an element of R, and X is not equal to Y, and Y, X is not an element of R. So the relation will become antisymmetric. We have got an XY as part of R, but this X and Y is not equal, like the situation is not 1, 1, right? Or 2, 2. And then Yx is not an element of R, which means whenever you have a 2, 3 and a 2, 3 and a 3, 2 is not part of R, it means that relation is now becoming a what? An antisymmetric. So a remark that you need to note, R is not antisymmetric if and only if there are elements A and B in A such that AB is an element of R and BA is an element of R, but A is not equal to B. So whenever you have this case where you have got AB and BA, you are going from this direction, then going back there, then the relation is no longer an antisymmetric. Then the properties of being symmetric and being antisymmetric are not negative of each other. You need to take note of that. They are not negative of each other. So it's not the case that if the relation is not symmetric, then you say it is antisymmetric. No, 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 no. There are some of the case where the relation can be not symmetric at the same time, cannot be antisymmetric. So consider the relation R on X, which is ABCD, which is given by as follows: A, B, B, C, and C, D. Then the relation is antisymmetric because for all xy, when xy is an element of R and x is not an element of is not equal to y, then yx is also not the element of R. If you look at it, we've got AB, we do not have a BA. We've got BC and we do not have a CB. We've got CD and we do not have a DC. Because of that, we can clearly say that this relation R is anti-symmetric. So you are no longer going back. So let's look at this relation on set 1, 2, 3, 4, and let's qualify them if they're anti-symmetric relations or not. Let's look at R1. Is it R1 and symmetric? Is it R1 and symmetric? We have got 1, 1, 2, 2, 3, 3. R1 is anti-symmetric because we have got a 1, 1 and a 2, 2 and a 3, 3. If you are looking at this, we do not have a case where we are going to have two vertex with the one going forward as well as going back. This one's just a loop back and this one's just a loop and this one just a loop. So it is both antisymmetric and symmetric. So if you look at it, it's both antisymmetric and symmetric. That's why we say that antisymmetric and symmetric relation, they are not opposite of each other. And then if you look at this one, R2, we've got the 1, 2, but here we do not have a 2, 1. Then we've got a 2, 2. Then we've got a 2, 3. Do we have a 3, 2 here? No. We've got a 3, 4. Do we have a 4, 3? No. We've got a 4, 1. Do we have a 1, 4? No. Which means this one is a what? Is antisymmetric. But look at it. It is not symmetric. Why? Because whenever we have a 2, 3, we have got not a 3, 2. If you look at that. So maybe to clear confusion, you need to take note of x not equal to y to qualify it for a relation whenever x is not equal to y. So you're neglecting for x is equal to y. That's why we have seen that whenever x is equal to y, we've got a 1, 1, we ignore the scenario that we must not have a loop back. So for a 1, 1, it's just a self loop. This one just a self loop. This one's just a self loop. So we can take it as unsymmetric. That's why you see that whenever we have got a 2, 2, we just ignore it. But whenever you have a 2, 3, you need to check if there is whenever you have a 2, 3, you need to check if there is a 3, 2. That one is the one that disqualifies it to be an antisymmetric. So let's look at what? At R3 is R3 and antisymmetric. We've got a 1, 3 and we've got a 3, 1. Whenever you have such a scenario, it means that this one, this relation is no longer an antisymmetric relation. So R3 is not what? Is not antisymmetric because we've got 1, 3 and a 3, 1. And also we've got a 2, 4 and a 4, 2. And then for R4, if you look at R4, is R4 antisymmetric? We've got a 1, 3 and a 3, 1. So it's not a antisymmetric because of that. So R4 is neither antisymmetric because 1, 3 and 3, 1 are present there. Also, it is not symmetric as well. Excuse me, because we have got a 4, 3 part. 3, 4 is not there. So that's how you check if the relation is antisymmetric. If there are questions, you can ask. Otherwise, we are going to look at transitive relation. It's about 7 o'clock. Okay, so we're going to look at transitive relation. So we need to look at functions maybe today, and then we stop there. And then next Wednesday, we'll look at other topics. I hope we finish. So let's look at transitive relation. If you do not have questions, I'm sure you do not. Richard Mufuro, is that a question?
Kumbira waka break say.
A what?
A small break.
A small break.
Yeah. Go visit agents.
Agents more gonna visit. I have to record. I need to travel just after this lesson. So yeah. I don't think I can give you a break. Maybe what you can do is just to go for just 5 minutes where I'm sure you catch up because the break roto datine mvura dzacho dzekunwira nditi kana zvimadrink zvacho. So for that one, you can just excuse yourself and then you'll be back. If you miss something, you can follow up on the recording. Okay, so on the transitive relation, A relation R on a set X is called a transitive if for all X, Y, Z are element of X, when X, Y, and Y, Z are element of R, then X, Z must be an element of R. So this one is a relationship which involves maybe three sets. You've got X, Y, and Z. And then whenever you have got X, Y, and Y, Z, you must also have X, Z. That's it. That's the transitive relation. And it ukama ukupiwa ne-hotspot and it kuti X na Y vanozivana, Y na Z vanozivana. It means X na Z vanofana kuzivana through what? Through Y. That's what we have done on a composition of a relation. So this is what we call the transitive relation. Consider the relation R on X, B, A, B, C, D, right? Which is given as follows: A, B, A, D, A, C, then B, C, then B, D, and C, D. This relation, is it transitive or not? So you are saying if you have A, B, and the B something, A must be related to that something. So you've got A, B, right? Do we have B, C? Yes, so you must have A, C. So if you have got A, B, and B, C, so A must be also related to C. Because A knows B and B knows C. So A must know C through the introduction by what? By B. So if you have got A, B, and B, C, so you must have A, C. So if you have got A, D, if you have got A, D, and D something, do you have D something? D something? No, we do not have D something. We've got AD. Do we have D something? No. Then we have got what? B, D. Well, also B is related to what? To D. So we've got AB, and then B is related to D. So we must have also AD. Yes. So AB, B is related to D. So we must also have BD, something like that. Then here we've got AC, and C is related to D, and then also you must have AD, something like that, and through C. So you must also have AD. So that's it. So from this, we can conclude that this is a what? This is a transitive relation. So on transitive relation, I don't know if I have question. I do not have a lot of relations that we can test for this. I just have one example here. So this is how we can qualify it to be a transitive relation. We just say it's through another relationship. So you have X, Y, Z, and then you look at relation between X, Y, and then Y, Z, and then you qualify X and Z through Y, just like that. So that's all on this relation. Maybe we now want to look at diagraph, which is like a diagram that you draw on relations. This one is very important, especially for assignment. It was there where you were supposed to draw a diagraph of a given relation, and then from there you could tell us if it is a reflexive or if it is something like that. If it is a reflexive, or if it is transitivity, or it is symmetric or anti-symmetric, by just mere looking at this diagraph. That's what we're supposed to look at. You just need to look at the diagraph and then it tell us. So one way to picture a relation on a set is to draw its diagraph. So a diagraph, a directed graph or a diagraph consists of two finite sets, which is a set of V of G, which is a set of vertices and a set of directed edges. So where each edge is associated with an ordered pair of vertices called its endpoints. So if edge E is associated with the pair VW of vertices, then E is said to be the directed edge V to W and is represented by drawing an arrow from V to W, just like that. So if you look at this one, we have got the vertices. So on this scenario, maybe on this scenario, these will become your vertices 1, 2, 3, 4, and then the edges now will be the direction that you'll be putting maybe from 1 to 1, then from 2 to 2, from 3 to 3, something like that. If I want to draw a diagram for this R1, the vertex that I have is 1, maybe 2, maybe 3, maybe 4. Then the diagraph will be a 1, 1, which means it will be a self loop. And then 2, 2, it will be a self loop. We are going from 2 to 2, and then 3, 3, it will be a self loop, Then this 4 is isolated. So if you are going to draw for this one, then you need to have 1, 2, 3, 4 as vertices, and then you put the arrows from 1 to 2, and then from 2, something like that. That's what you'll be doing. So here, this was just an example. Richard Mufro, do you want to say something? Do you want to contribute? I'm seeing a hand, or it was just raised before.
Oh, I had raised it before. Sorry, sir.
Okay, it's okay. So that's that's how you draw this diagram. So let's look at this, which is characteristics of a relation and diagram. This is the concept that you need to use when you're answering the question which was in your assignment, which was asking you to draw a diagram, and then from the diagram you deduce if it is reflexive, or if it is transitive, or if it is symmetric, or it is antisymmetric. So on a diagram, if it is reflexive, you have a loop at every vertex. There's a loop at every vertex. Then from there you can say that this is what? This is reflexive. Then if it is symmetric relation, it has the loop at that whenever there is a directed edge from V to W, there is also a directed edge from W to V, just like that. So if you've got the one going from V to W, must also the one going back from W to V. For an antisymmetric, is the property that between any two vertices there is at most one directed edge. And then for transitive relation is the property that whenever the relation there are directed edges from X to Y and from Y to Z, there must be also a direct edge from X to Z. So this is what you need. This is what you need to hunt for when you're answering that question. That's what you need to hunt for. And then for the, so I think for drawing them, it's very, very simple. Maybe I can draw, which one? Let's go maybe for this one. Want to check if this one is too big with the space that I have. Let me take for this one to check if it is symmetric. Maybe which ones? R2 is also symmetric. R2 is R2. This one. The other one which is symmetric is R1 symmetric? Okay, let's do for R1. Okay, let's do for R1. So I've got 1. Maybe I've got 2. Maybe I've got a 3 here. Maybe I've got a 4 here. All right. So normally you circle them. This is a directed graph. This is how you draw a directed graph. Right. So let's look at R1. Here we've got a self loop at 1, 1. Right. This is a self loop at 1, 1. Then you have 1, 3. From 1 to 3. From 1 to 3. This is from 1 to 3. And then we have got 2 to 4. From 2 to 4. And then we have got 3, 1. From 3 to 1. You see, we've got 3 to 1. And then we've got a 4, 2. From 4 to 2. So this one, by just looking at this diagram, you can tell us that this is a symmetric relation. Why? Because whenever you've got a directed edge from 2 to 4, you also have something from 4 to 2. Whenever you have 1 to 3, you also have 3 to 1. So by just looking at this, you can conclude that this is a symmetric relation. So I want you to comment using this. When you are commenting, you need to tell us this is a symmetric relation. Why? Because at 2, we have got an arrow going from 2 to 4, and also we've got an arrow going backwards from 4 to 2. Also, whenever you've got an arrow going from 3 to 1, we also have an arrow going from 1 to 3. Just like that. That's what you are supposed to do. So let's look at those relations of partial order, and then we do equivalence relation. This was also part of your assignments. I think it was part of your assignments. So those relations of partial order, a relation R on a set X is called partial order if R is reflexive, antisymmetric, and transitive. So if you're being asked to qualify if a relation is of partial order, just need to confirm, is it reflexive? Is it antisymmetric? Is it transitive? If it can be of these types, then you can say that this relation is of partial order. So consider the relation R on set X 1, 2, 3, 4, 5, and defined by XY is an element of R if X divides Y. So if we've got this relation, whenever X divides into Y, which is we've got 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, then 2, 4, 3, 3, and then 4, 4, and then 5, 5. Then need to qualify, is it R reflexive? Is it R antisymmetric? Is it R transitive? If it is true, then you can say that R is of partial order. So that's how you answer this. So the first thing you check, is it R reflexive? You check for reflexivity. So if you look at it, we've got 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Then which means it's reflexive because we've got this 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. Then is R antisymmetric? If you look at it, since we have got a 2, 1, 3, 1. Since here we've got 1, 2, right? We've got 1, 2. Do we have a 2, 1 here? No. We have got a 3, 1. Do we have sorry, we've got a 1, 3. Do we have a 3, 1? No. We've got a 1, 4. Do we have a 4, 1? No. We have got a 1, 5. Do we have 5, 1? No. Same here, we've got a 2, 4, but we do not have a 4, 2, which means R is antisymmetric. Right, and then for transitivity, whenever you have what? For transitivity, we have 1, 2, and then 2, 4, and 1, 4 are in R. Let's look at it. We've got 1, 1, then we've got 1, 2, 1, 3, then 1, 4, then 1, 5, 2, 2, 2, 4, 3, 3, 4, 4, 5, 5. Why is this one a transitive relation? Why is this one a transitive relation? Because we're saying we have 1, 2, and 2, 4, and 1, 4. Then we are saying this is a transitive relation. Why is it a transitive relation? Why is it a transitive relation? Someone to try? Why is this one a transitive relation? Lynette? Yes, Lynette.
Okay, I think it is a transitive relationship because we've got 1, 2, and then we continue, we find there's another vertex with which continues from 2, which is a 2, 4, and
Yes.
then the next vertex is which will be a what? A relationship from 4. Is it a 4, 1? Sorry. No, I don't see a 4, 1. Yes. So I think it's a continuation of vertices from one vertex to the next.
Exactly, that's it. So you are saying whenever you are having a 1, 2 and a 2 something, then 1 must be also related to that something. So we have 1, 2, and then we have 2, 4. So this one must be also related to 1, 4. Then because of that, then we can say that this is also a transitive relation. So if you have 1, 2, and then you have 2 being mapped to something, this one must be also mapped to that thing, something like that. So which means that this is a what? This is a transitive relation. So after confirming that, you have confirmed all these relations, reflexive, antisymmetric, and transitive, then you can say this one is of partial order, just like that. Then for equivalence relation, just need to confirm if it is reflexive, symmetric, and transitive. So you just need to see that here we are talking about antisymmetric with the transitive and reflexive. But here we are talking about reflective, symmetric, and transitive. So that's the difference. On equivalence, it needs to be symmetric, reflexive, and transitive. So that's what you'll be looking at. So for example, we have got this relation R that we have on this set. So you need to confirm if it is reflexive, if it is symmetric, and if it is transitive. And then you say that this relation is what? Is an equivalence relation on the given set. So the first thing for reflexivity, we are saying we've got a 1, 1. We must have a 1, 1, a 2, 2, a 3, 3, a 4, 4, and a 5, 5, just like that. And after that, you check for symmetric. Whenever you have a 1, 3, you must have a what? A 3, 1. Yeah. Whenever you have a 1, 5, you must have a 5, 1. Whenever you have a 2, 4, you must have a 4, 2. 3, 1, you must have 1, 3, or something like that. So it will, then you can conclude that R is symmetric because whenever XY is in R, then YX is also in R. So that question in assignment, where you were being asked to show that equivalent, is it an equivalence relation? That's what you need to comment. That's how you comment. Then you check for transitivity, saying, because whenever X, Y, and Y, Z are in the relation, also X, Z is also in R. So we are saying here we've got 1, 3. You check if there is where 3 is being mapped to, like we've got 3, 5, right? We've got what? It's transitive. We've got 1, 3, and then 3 is mapped to 5. Also, we must have a 1, 5. Do we have a 1, 5? We are having a 1, 3, and then we've got a 3, 5. Do we have a 1 mapped to 5? Okay, here we have it here. Something like that. So you need to check for others. We have a 2, 4. Do we have a 4 mapped to something else which is not 2? So that's what you'll be doing. So if you have a 2, 4, and you have a 4 being mapped to what? We do not have anywhere where 4 is just being mapped to 2 itself. So it's already that 2 is mapped to 2. So it's a transitive relation. So that's what you check there. After that, you can conclude that this one is in what? Is an equivalence relation. So I don't know if I've got questions on relation. Do I have questions on relation or a contribution on relation? Do I have questions or a contribution on relations? Questions or contributions?
Yes,
Yes, Tagus.
yes, I've got a question.
Yes.
Is it possible for a reflexive relation to be automatically a symmetric relation?
A reflexive relation to be
automatically a symmetric relation?
From reflexivity to it's not obvious. It's not obvious. It's not obvious that if it is reflexive, then you're asking between reflexive and symmetric.
Symmetric.
Yeah, it's not obvious that if it is reflexive, then it's symmetric. Because when it's a reflexive, we're just looking at is it having all the elements in the set mapping to themselves. So you must have other junk within that relation. So which might be not conforming to symmetric relation.
Okay.
So it's
Thank
not always the case. Yeah.
Okay.
Okay. So
Thank you.
maybe okay, you're welcome. So maybe now we just need to okay, maybe what I can do is go and read on we're supposed to do functions, right? So go and read on functions. On our next tutorial, we're going to start on functions. I'm running out of time, so just go and read on functions. It's very, very important because it's part of your exam. We ask you all those questions because they are part of your module. So you need to look at what? You need to look at functions. So read the slide on functions. On the next tutorial, I'm going to start on functions. I don't know if I have questions before I go. Don't know if I have questions. Yes, Walter, you want to say something?
Ise tokumbirawo patime apa ndoona sekuti time dzekuma sezvinenge dzataita network traffic yacho inenge yakawandira inenge ichingodropa drop saka tizivi mukatisuggestirao imwe time yekuti vanhu vanenge vasiri busy nenetwork still.